Hi, this is section 1.6 on atomic orbitals. This is where your book delves a little bit into the history of quantum mechanics and starts to talk about where electrons are physically around an atom. There's a decent little write-up about the history here and the math about the quantum mechanical description of electrons, but there isn't much detail given, and that's because quantum mechanics is extremely complicated, and to try and go over the even just the basic beginnings of statistical mechanics and how that deals with chemistry, it would take us a whole semester. And in fact, there is a whole class on this in junior or senior year, I believe, for chemistry majors. So I just want to show you that I'm not just like, trying to show off or something for you all, because this is a basic quantum mechanics book that I can show you that describes in the very barest of details what the Schrodinger equation is. That is, how to find either the position or the momentum of an electron, but not both. So you can see here it's a lot of math, and it is outside the scope of this course. So what we won't do is we will not touch on this very much. But what we will do is we'll talk a little bit about how orbitals matter for us in organic chemistry, and specifically how the s and the 3p orbitals matter for us. And they matter greatly because depending on where an electron lies in space, such as how these orbitals are drawn, will depends or really affects the reactivity of atoms and molecules. So let's have a look at electron configurations. I'm actually going to go over to the notebook here. There we are. Okay. Because this is kind of key. Right. So as you just saw, we have, let me switch over to this will be back there. Right. So we have the x-axis, y-axis, and z-axis. Okay. The simplest type of orbital is an s orbital, and it's kind of a sphere that goes around in every plane. Okay, and this is where the 1s, I should do that in green, where the 1s, here energy is increasing, and 2s orbitals lie. But then we start to have, oops, oh, let's see. There we go. Then we start to have some orbitals where you can have, let's do it here. You can have positive electron density and negative electron density. And so this is one type of p orbital, only in the y and the x direction. But you can also have an orbital that is in the z x direction. Hopefully you can kind of see that. And you can have one that is in the, so I guess that's the first one was y and z. What I'm trying to illustrate is that they have three different ways of existing. And maybe I should just go back to the book for that because they have a pretty good drawing. So let's do that. There we are. So you can see here, py in the y plane, px in the x plane, and pz in the z plane. That's what I was trying to draw in the notebook. So anyway, what we're going to do is talk a little bit about the electron configurations, because drawing the electron configurations is very important. As we see here, I'll go back to the notebook. If we drew the electron configuration for carbon here, we have energy increasing, and carbon has 4 valence electrons in the in the second shell, but it also has a 1s shell. So 1s, 2s, and 2p orbitals. There are 3 of the 2p orbitals, and carbon has 6 electrons, 2 in the first shell and 4 in the second. So we would use the 3 rules, which are the Aufbau principle, saying that the lowest energy level is filled first. So we would do 1. Let's do this in different color. We would say 1, 2, and we drew the second one pointing down because the Pauli exclusion principle says that if you have an electron in one energy level with one type of spin, the next one has to have the opposite spin. So we do 1 up and 1 down. Now, the spin, it's our nomenclature. Electrons don't really spin. They're more of a, that's just a way that we express that one is oriented one way and one the other. They would cancel each other out. So that's why we have them here. So going to the next energy level, we have 2s electrons, and then we would have again these next 2 electrons, which completes the valence set. And Hund's rule tells us that if we have degenerate orbitals like these 3, we have to fill all of them sequentially. So we add 1 electron to the first and then 1 electron to the second. However, this would mean that only 2 electrons are available for bonding. So that means that drawing a carbon with this configuration would end up looking like this, right? So that type of configuration, well, I guess here's the other 2. They're already together. In this type of configuration, this carbon cannot make 4 bonds. And we already said, and we've already seen in several classes before, carbon makes 4 bonds. So how can we make carbon have 4 bonds? Well, this is one of the magics of organic chemistry and why it is so interesting. I'm going to take this stuff. I'm going to just move it down here. There we are. Oh, 2. There we go. Okay. Because this, as you might imagine, is a very high energy arrangement. Carbon wants to make 4 bonds, in as much as an atom can want to do anything. The energy related to making 4 bonds is so high that carbon, that if it can, carbon will do that. But the reason why it will do that is because of this. Right now, we have 2 half-filled degenerate orbitals and 1 empty. But we can actually lower the overall energy of all the orbitals by doing what's called hybridization, or by hybridizing all 4 of these second shell orbitals, all the valence orbitals possible. So if instead we make a diagram that looks like this, where energy is increasing, and we have the 1s that's filled with 2 electrons like before, but now we combine the s and the p orbitals to give them all equal character, then we create what's called a 2sp3 set of orbitals that have 4 degenerate states. And so now, due to Hund's rule, we can put one orbital in each of these degenerate states, and the carbon we would draw using these states has those 4 valence electrons like we talked about. And now this carbon can make 4 bonds. So a funny coincidence of this, if we go back up to the top here, you saw how I drew that the s orbitals are spherical and the p orbitals have this node shape. Well, we just combined all 4 of these. So now all 4 of them have characters of both s and p orbitals. But what does that mean? So let's draw these out again. So let's imagine we have a sphere for the s. I should do it in the light blue again. We have a sphere for the s. And for the p, we have a large blue here, okay? So now if we are going to combine these two, let's say that we're going to combine them and we're going to make that into green. I'm going to overlay it with green here. There we go. Okay, so now we have this s orbital overlaid onto the p orbital, right? Something that we didn't talk about is that the s orbital is all either positive or negative. There's no in between like in the p orbital. Because remember, in the p orbital, one side has to be a positive and the other side has to be a negative. It doesn't really matter which is which, but one has to be one and one has to be the other. Whereas in the s orbital, it's either positive or negative. So when we overlay, when we mix the s with the p, remember that this s and the green s is the same. When we overlay those two, let's say that this is positive and we have a positive side over here. This positive s orbital is going to increase the magnitude of the positive side of the p orbital due to constructive interference, meaning it's going to get bigger. That's what we would call it in physics anyway. Whereas on the other side, it's a negative. It would cancel out that positive. And so you have destructive interference with the p orbital, which means that this side of the lobe will get smaller. So that means when we do mix these two together, the orbital we get looks really weird because one side is big due to mixing with the s orbital, and the other side is really small due to destructive mixing with the p orbital. And you have 4 of these because we just made 4. So now this is the sp3 orbital. And if we were to draw this, or do my best to draw this, you would see that the sp3 orbitals, when you put them together onto a carbon atom, here's our carbon atom, would look like this. Kind of like a weird little balloon animal. And this is how the carbon makes all 4 of those bonds. So this is a good primer onto atomic orbitals. There's some more in your book about electron configurations and a little bit into hybridizing too. I kind of jumped into the hybridizing part of atomic orbitals, but this is a good place for us to stop. So this has been section 1.6 with a little bit of 1.9 thrown in there as well.